Welcome back to Antiformal. My name is Bryn Cable, your host, and today we will go through some upcoming events, the mineral of the day, and then an interview with a very special guest. So up first, we have club events. We will have the general meeting Thursday, November 11th at 7 p.m. Our next mineral auction will be Monday, November 29th, 9 to 5. And recently, we volunteered at the Oklahoma Mineral and Gem Society show, Gems and Stones and Petrified Bones, where we identified hand samples for people who bought things at the show. We played mineral match with our visitors, both young and old. We talked about special properties that some minerals have, like effervescence or luminescence or fluorescence. And we provided some hand samples for the public to examine. Before the mineral show, we hosted Geology Office Hours with Dr. Molly Yunker at the Oklahoma Geology Survey, where citizens brought in samples for us to identify. One man thought that he had 2 meteorites. Neither were meteorites. Another woman found what appeared to be some Native American playing marbles. They were very round, very smooth, very interesting. And we even used the rock saw to cut open a specimen for one person who brought in a really cool agatized rock. And it was a great morning. We got to see a lot of people, a lot of rocks, and I hope we have another one soon. Our mineral of the day is kyanite. Kyanite is typically blue. It is an aluminosilicate found in aluminum-rich metamorphic pegmatites and sedimentary rock. It is the high-pressure polymorph of andalusite and sillimanite, and the presence of kyanite in metamorphic rocks generally indicates metamorphism deep within the crust. The chemical formula is Al2SiO5. Kyanite is mostly found in metamorphic rocks, but it often forms as the high-pressure alteration of clay minerals during metamorphism of sedimentary rocks. And it's usually within the schists and the gneisses of regionally metamorphosed areas, and less often in quartzite or ecliptite. The typical crystal habit is bladed, although sometimes it occurs as radiating masses of crystals, and kyanite is often associated with other metamorphic minerals such as garnet, starlight, and corundum. Kyanite is the high pressure polymorph of sillimanite, so that means that it is on the top of the triple point graph, and sillimanite is at high temperature, andalusite is at the low pressure, and kyanite can actually expand up to twice its original volume when heated. So here is where you can see that bladed crystal habit. This specimen is $8. Each one of those is its own individual blade. And of course, we're looking at the blue part of the specimen, not the white quartz. The evidence of twinning. Here, you can kind of look down the blade axes. Because kyanite forms at such high pressure and temperatures, it's used in a lot of porcelains because it's so heat resistant. And that is the mineral of the day. And now it is time to invite our lovely guest. Hello.
Hi.
Today we have Lynn Soreghan on our show. She is our director at the School of Geosciences. She did her undergrad at the University of California, her PhD at the University of Arizona, and we've brought her on the show to share a little bit of her expertise.
Well, thank you for inviting me.
Yeah.
I'm happy to be here.
We're happy to have you. Could you start by telling us a few differences between the universities that you've been at?
So UCLA, which I grew up near UCLA, so that was just sort of a, natural place for me to go. So they're all big state schools. I would say there are differences sort of at the almost the feeling of the school itself, that the whole campus versus the departments. Say the departments are very different. So say UCLA was a department it's actually called the Earth and Space Sciences Department.
Okay.
So there was quite a bit of planetary sciences that went on. So the disciplines were very different from what I experienced in other places. So a lot of space sciences, and then a lot of hard rock geology, igneous and metamorphic petrology. My initial sort of love was metamorphic minerals because they were really pretty under the microscope, you know, fuchsias and blues and all this kind of thing. And in fact, so disciplinary wise, the geoscience was very fundamental geoscience, hard rock, you know, tectonics kinds of things, in space sciences. And then in terms of the school, you know, I mean, football was kind of sort of a thing, but nothing like OU, right?
Nothing
So
like
in
OU.
terms of the campuses, OU wins by far and away in terms of the importance of football and just, you know, and even kind of the spirit of the school. I would say that there's a much, you know, there's a lot of just spirit when you walk around and so forth. Going to Arizona somewhere also not, probably even less in terms of football. I don't know if that's really true, but to me, I guess it seemed like that was kind of less of a presence. And that school was very much into both mining and then also tectonics. And I went there because I wanted to work with an advisor who did sedimentation and tectonics, which was sort of ironic because I came out of the school that was hard rock, not soft rock. And my very first soft rock class, I hated. And it turned out that I was not into it because the pedagogy wasn't very good, frankly.
Oh no.
So the teacher wasn't the greatest. But then I took another class called Sedimentation and Tectonics, taught by an excellent professor named Ray Ingersoll. And I just found it fascinating that there are so many things that you could tease out about the earth using sediments, you know, and the focus of that was tectonics. So it was like, wow, I can, you know, reconstruct where mountains had been built and so forth using just sand grains. And I thought that was so fascinating. So I ended up going to Arizona, and Arizona was more of a school that was really, at the time, both had a mining focus and also really a growing program in tectonics. And I just found that really, really fascinating.
Okay.
They now have a very strong emphasis in climate and paleoclimate as well. And that was kind of, I would say, it wasn't beginning, it was just different. There was a very strong quaternary paleoclimate group. And then they had someone who did basically deep time paleoclimate. And so I started to get exposed to that side of things there.
Okay, very nice. Thank you. When you were doing your undergrad in California, what kind of undergrad research did you do?
Okay, yeah. So as I said, I became really fascinated with how you could look at sand grains and interpret like massive orogenic events and basically reconstruct plate boundaries using essentially counting sand. And that was what my advisor, my undergraduate advisor, Ray Ingersoll, really specialized in that. So he would look at, you know, we would look at sandstones. And for example, we did a project where we looked at sands from the Great Valley sequence in California. And you could literally see the unroofing of the Sierra Nevada mountains and the basically the transition from a subduction zone to the San Andreas Fault by looking at the sand through time. And I thought that was so cool. And so I was basically convinced that I wanted to do something like that and look into that more. And as a grad student, what we ended up doing was going out to Santa Catalina Island and collecting sands, modern sands, from the island, and basically looking at reconstructing sort of the tectonic setting by looking at the sand grains.
Okay.
So it's sedimentary provenance analysis using, you know, just QFL, quartz feldspar lithics.
Yeah. And how does that tie into what your current interests are and your current research is?
Yeah, so I went to Arizona to work with, as it turned out, Ray Ingersoll's former advisor, graduate advisor. His name was Bill Dickinson, and he had worked for most of his career at Stanford University, and he was very instrumental in the plate tectonics revolution. So he was basically a big player in the discovery that you could reconstruct plate boundaries and really how to think about plate tectonics, as opposed to, remember that plate tectonics was still not really an accepted theory, right?
Yeah.
It was really ramping up in the late 60s and the 70s, before people, especially on the East Coast, really accepted plate tectonics. That was something that Ray Ingersoll used to joke that the West Coast geologists accepted plate tectonics much sooner than the East Coast geologists because they lived it, right? They were on the plate boundaries. But Bill Dickinson, his role in that was really connecting sedimentary geology and especially sandstone provenance analysis with reconstructing plate boundaries. And after much time, basically his whole career, in fact, he got all of his degrees at Stanford and then became a professor at Stanford. And he stayed there until about 1981, and then he moved to the University of Arizona. And so I grew up, as you will, sort of, so to speak, under Ray Ingersoll's tutelage, and we read all these papers by this guy named Bill Dickinson. And his papers always had these really easy to understand diagrams about plate tectonics, and it seemed so clear to me that I was like, wow, I really want to, work with this person.
Mm-hmm.
So that drew me I went to Arizona specifically to work with this person, Bill Dickinson.
Okay.
Well, yeah, how does it tie in?
Yeah.
So I started and I met with Bill and I said, I really want to do this kind of research. And he said, okay, but you don't want to just go out and measure a section of rocks and just reconstruct the tectonics, because that's been done a lot. So, so what else could we do? And he actually encouraged me to play a role in choosing what I wanted to work on. And so at the time, which was the late 80s, early 90s, one of the things that was going on in sedimentary geology was trying to really disentangle the effects of tectonics from the effects of sea level change in rocks. It was a time when, we're talking about this in class right now, sequence stratigraphy, and there was a lot of talk about, well, what's more important, tectonics or sea level changes, and are they eustatic or not, or are they, basically relative and so forth. So I really wanted to work on that. So I kind of designed a project that where I was looking at rocks in a few different sedimentary basins, so different essentially tectonic settings, and trying to correlate them very closely and trying to disentangle the effects of tectonics from other effects. And so the focus was tectonics, right? But it just so happened, and it didn't relate much to what I did as an undergrad, to be honest, other than the connection to using sedimentary geology to look at tectonics, right? But the more I got into it, the more I started to think that climate was a really big role in these rocks. And the reason is because the time period that I happened to choose to study was the late Paleozoic, the Pennsylvanian Permian. And of course, we now know, we've known for a long time, actually since the 1800s, that was a time of large ice sheets on the planet. And so there are sea level changes recorded in these rocks, right? Glacial-eustatic sea level changes. But of course, the sea level changes are simply a reflection of a massive climate change on the planet, glacials and interglacials. And so the more I looked at these rocks, the more I was thinking, wait, there's a really big climatic component to these rocks. So yeah, there's tectonics and there's sea level change, but also climate going on. And I have to laugh because I went to Bill, and I said, I think that, climate is a really big role here. And he's like, well, and he was this big, tall, kind of cowboy kind of guy, and he's like, yeah, but tectonics paints the broad brush strokes and climate is the flute music,
Oh.
So anyway.
The flute music.
The flute music, yeah. But it's not such flute music anymore. Yeah.
Well, did you have any big surprises during your transition from schooling into working?
Into working. Let's see, big surprises. We talked about this a little bit before, but now I'm thinking about it more deeply. And maybe the biggest surprise is, I feel like in graduate school, it's very much me time. You're doing it all for your interests and trying to get your degree and all that. And especially as a professor now, you're split so many different ways. So that's one of I think a big surprise is trying to figure out how to manage time on an even more frenetic schedule.
Okay.
Because I think as a student, you are hit with a lot of different demands, and you're taking multiple classes, and so there are a lot of demands as a student, and trying to time manage as a student is a really hard task. And then becoming a professor, I just didn't quite appreciate all the different roles that I would play.
That a professor plays. And almost like as a student, you have a lot of deadlines that are set by other people.
That's right.
And then as the working person, you have to set the deadlines and abide by them. So
Right.
It's kind of a double whammy.
That's exactly right. Yeah.
What is your favorite mineral and why?
Well, I've been thinking about this one, and I was like, oh my gosh, this is like asking me, what's my favorite place I've ever visited, or what's my favorite national park, or like I can't choose.
They're too good.
Because
There's
I'm
too
a
many
geologist, right? It's kind of, in fact, I think that when I think back on what got me into geology, I think back on things like 7th grade, how in 7th grade you get like a little snippet of all the different sciences. And so, you have an earth science unit. And I remember playing with mica.
Yeah.
Right? Because it was like so cool. These sheets that you could peel, and you could crunch it up and like rub it on your face, and
Make your own
look
eyeshadow.
through it. Yeah. And so like mica has always been a big attraction, just
That's a
because
good
I think
one.
it's just such a fun mineral to play around with, and it has so many uses when you start to realize it. But now with kyanite sitting all over the table, I have to say that one is super cool, just because there's so many different forms of sillimanite and kyanite and andalusite, and it's metamorphic, and so that's pretty good too. So it's really hard to choose.
It is really hard to choose.
Starlight is a good one.
Yeah, that one is a good one.
Yeah.
What is an unsolved geologic problem that you find interesting?
So stemming from the time that I was in grad school, and I was studying, some of the places I was studying were mostly carbonate platforms. But I was getting these incursions of silt, and it was kind of mysterious because there were no rivers to bring it in. And ultimately, the short answer to this story is that I ultimately interpreted these things as aeolian deposited, so loess, right, windblown silt coming into the system. But it was very interesting because I would get the limestone, and then say an exposure surface, in other words, a glacial, interglacial, then glacial, sea level fell, right? And then I would get this loess blown in, and then I would go back to the carbonate, right? So there were these carbonate silt cycles in essence, and that really captured my, I guess, imagination, because I started delving into the literature on loess, and it's a very big quaternary literature because it's a well-known deposit on the planet today. It covers 10% of land on the planet. And it's largely, not entirely, but it's largely made very efficiently, let's say it that way, by glacial grinding. It's not the only way to make it, but it's a way to make large volumes of it. And as I started to, when I came to OU, I started getting more interested in paleoloess, deep time loess. And as I started studying it more and more, it was like, well, there's really a lot of this stuff in the Pennsylvania Permian, and there's a lot of it here in a part of the U.S., like modern day U.S., that would have been at the equator during that time, right? And so I started wondering about the possibility of whether there could have been glaciation in the highlands, at low latitudes. And that's something that I've been, I think, sort of ridiculed a lot for, because it's not a, but it led me ultimately to go to places to look for evidence. Now, the problem is, how do you look for evidence of glaciated highlands when the highlands are no longer there? They've been, eroded. So I thought, okay, well, I'll go to the places that were closest to those mountains, right? And that led me ultimately, I kind of stumbled across this place called Uinta Canyon in Colorado. And I've been studying that place on and off for about 20 years, because we have this hypothesis where we think that it may be a paleo landscape. And the paleo landscape, we think, may have been carved by glaciation
Okay.
during the late Paleozoic. That is, Unaweep is a very strange canyon. It's said to be the only canyon in the world with two mouths. So if you drew a longitudinal cross section through the canyon, instead of going from a high point to a low point, instead it goes up and then down, and there's a high in the middle of the canyon.
Wow.
And that's I've heard that that's the origin of the name Unaweep, because it's a Ute Indian name, meaning either, I've variously heard, tears on both cheeks, or parting of waters, or
Wow.
canyon with two mouths. So it's been this mystery, and we've done some research over the years that have led us to hypothesize that it's a partially exhumed paleo landscape. So there's still quite a bit that's buried. And we've done some seismic work now to show that there's quite a thick section in the subsurface. And now we're very close to the acid test of the hypothesis, which is actually trying to drill and core into it and see what we pull up, and see if this is totally wrong, which it very well could be.
If it's not wrong, what would you be expecting when you
So
pull it up?
if our hypothesis is correct, then we would expect that at depth there's actually strata of late Paleozoic age that is either of glacial origin or proglacial origin.
Okay.
And so we'll see what happens. It's going to be exciting.
Is this what you were talking about missing class for? Is this
Right.
drilling?
Yes.
Wow. So it's coming up.
It's taken a long time to get there. Yeah.
Wow.
Yeah.
Okay.
It took me about it's expensive to core, so you have to write a proposal. In our case, we wrote a proposal to the National Science Foundation, and I first started writing those proposals to core in 2015, and you can only resubmit annually. So you can't. So it gets rejected. If it gets rejected, which this one did. So this one is my personal best or personal worst in terms of the number of rejections. So it was rejected 6 times, 6 years in a row, and then it finally got funded on the final try. So, and then COVID delayed it, right? And COVID has delayed it for now almost 2 years, and so hopefully we'll have an answer at some point. So,
hopefully soon.
Yeah.
I might invite you back if you do get an answer.
Then it's going to be either, well, it'll be interesting one way or the other, right?
Yeah.
It'll either be, well, we were totally wrong and we never could have dreamt it up, but this is what happened, or maybe we'll see. Yeah.
I wish you the best of luck.
Thank you.
You've said deep time a couple of times, so could you share what your definition of deep time is?
Yeah, that's such a good question, because it does have different definitions for different people. So to me, I usually apply it to mean pre-Cenozoic, even pre-Quaternary, because, for example, as my research, which really comes from the geological side, as my interests have gotten more climatically inclined, if you will, I started teaching classes, for example, in Earth's past climate and so forth. And when you teach the near time record, there's really high resolution. We know a lot of what was going on. There's still a lot of really deep mysteries in terms of, and when you asked questions earlier about what's a big geologic question, there are some really interesting questions about near time climate. But to me, there shouldn't be this wall between near time and deep time, and I think the wall is breaking down between the two. Okay. But you asked just the simple question of what's deep time, and to me, deep time is really thinking geologically, thinking about the geologic record. Even when you're talking to a layperson on the street, when you start talking about 2 million years ago, that's probably deep time to them, yeah. Right? But there has been this kind of artificial wall. For a long time, there were even, there still are journals called Quaternary Geology. I mean, you were a Quaternary geologist if you studied kind of the near time, right, the Quaternary record. Mm-hmm. And part of that was because the dating methods that we use to date, the recent record are in general different from the dating methods that you use to reach into deep time, and the resolution is hugely different. Now, as instrumentation is getting more powerful, and people have come up with really creative ways to attack that problem. It's getting a little bit easier. The resolution slowly is going up of even deep time states. But anyway, that's kind of what it means to me. I still kind of consider it loosely pre-Quaternary or even pre-Cenozoic when you get into really deep time.
Okay. When you're talking about the different ways that we measure deep time versus near time, is that just the different elements that we're using in the half-lives, or is it different systems altogether?
It is, well, at both, actually. So for example, when there's more than one uranium lead kind of system to use, sorry, and so there are and those generally tend to have the really long half-lives, right? And so, for example, we do, say, detrital zircon dating, and you can use, there's a couple of different systems, and you can co-plot them so that basically you can tell whether the age is good or not because you've got two different systems to use, right? You could never use that uranium lead system in near time because the half-life is so long, right? So in really near time, like in this morning's seminar, we were talking about carbon-14 dating, right? Carbon-14 has a half-life that's, roughly between 5,000 and 6,000 years. And so you can go about 10 half-lives, but when you get to trying to date things that are, roughly 50 to 60,000 years or older, it gets pretty tough because you've got a lot of daughter at that point, but very little parent element left, right? So you can't really use carbon-14 to date things that are 200,000 years old, And for a long time, there was a real gap there where the long half-life elements were too long to use in near time, and then the short half-life ones tend to be ones that are created in Earth's atmosphere essentially daily. They're cosmogenic nuclides, so that's why carbon-14 is a cosmogenic nuclide. And there have been some really creative ways to look at other cosmogenic nuclides, as well as things like optically stimulated luminescence. Have you heard of that?
I haven't.
OSL. It's basically when you bombard, when a quartz grain is sitting at the surface and being bombarded by sunlight, it's being stimulated as well, and there's this optically stimulated luminescence. And once it gets covered up, then there's this essentially half-life that begins there. This clock starts ticking. And so, and I'm not well versed in it, but essentially when you go out and sample for OSL dating, you have to keep the sample in the dark until you then go and measure it. But there are different techniques to try to get it at near time.
Wow.
And yeah.
So the light that stays inside the quartz crystal, or the luminescence,
it's it stimulates. It's optically stimulated luminescence. So it luminesces as a result of being bombarded by light, but then that luminescence kind of dies over time, right? And so it's a measurement of, I suppose, the level of luminescence.
Okay.
Left. Yeah.
I'd never heard of that. That's really interesting. Is there a certain thing that you look for in the field that can signify, like, oh, I am looking at some deep time right here?
That's an interesting question. Go look at the Pleistocene in California, and sometimes it's not very, or even here in Oklahoma for that matter, and it's not very well lithified. They're clearly, if it's been a bit metamorphosed, right, a metasediment, you might think, but again, that doesn't have to be old, it depends, but commonly, the older the rock gets, the more it might be subjected to something like that. So, lithification levels, and how much it's been through. And to some degree, sometimes, and these are all generalities because I can also think of things that are remarkably not like this, but for example, in California, it's very tectonically active there. So there's a place called the Ventura Anticline, and I think they're Pleistocene rocks, but they're actually folded. And that's kind of remarkable, right? Because it's very recent tectonic activity. Usually when you see things that are really folded and deformed, you think, oh, this has been through some stuff.
Yeah.
But it needn't be that old if it's in a tectonically active place. And by the same token, here we're in the mid-continent where you've got Paleozoic rocks that are flat-lying, right? So everything has a counter argument for it. But I've even seen Precambrian rocks that will crumble in your hand. So it's kind of interesting.
That
it's
is
not
interesting.
Not always. Actually, it reminds me of one of the first times I went to Unaweep Canyon, and we were looking at we were looking at the map, and I was looking around and I was thinking, well, according to the map, we're in Permian rocks here, but it was like a sandbox. They were all very, friable, and I said, I mean, could the map be wrong? Could these be Quaternary? But they weren't. They were Permian rocks. So,
Okay.
it's hard sometimes, yeah.
I know that you're passionate about promoting diversity and inclusion within our school. So do you have any ways that individuals can work on being more inclusive? Like advice or book recommendations or...
Yeah, I think that I've been doing a lot more reading. I think that reading some of these books, and we've talked about a few titles here in Oklahoma that blanking out again. Flowers of the Killer Moon book was really fascinating and very relevant for here in Oklahoma. Looking at some of the things that have happened to how we've treated the Native Americans, right? And then white fragility, but we've actually got a whole library now in our department. And one of the things I've found helpful is doing book clubs, right? So reading, and not just books, but even just articles, right? And then coming together and talking about them and getting different people's perspectives, because everybody's bringing a different life experience. People of color bringing their experience as a person of color, people from different cultures, people from different economic backgrounds, right? And people from backgrounds where accessibility is an issue, physical accessibility and so forth. So I've really found it enlightening. I've done a couple of things in the past year that were really great. One was participating in the URGE program, which was undoing racism in the geosciences. So we had groups, inter-college groups, and so we met people from, we're doing it on Zoom, and that worked well, right? And so we were meeting people elsewhere on campus. It attracted people from different backgrounds, and so that was really rewarding. Of course, OU's got a lot of the Unlearning series, and doing those was really eye-opening as well. And then the books, I think there's both personal growth that can happen, but then personal growth in a group setting. And it's really nice too when you can lay down some ground rules and say, okay, we're gonna talk openly because we all bring different experiences here, and we're not gonna chide somebody if they say something a certain way, and we're going to keep our discussion in this group, and we're not going to go outside this group and talk about, you should have heard what so and so said, so that people can be open and not be put down for anything they say, because I think there's a lot of fear of what's being said. We're trying to be a learning community, so I think these discussions and book clubs that incorporate people of diverse backgrounds are really, really helpful.
Yeah, I can agree to that. Thank you for sharing. Do you have any kyanite facts? It is our mineral of the day.
Oh my gosh, kyanite facts. Oh, I did not prepare. I feel really lucky that this is Kyanite Day.
Yeah. I found out today that the hardness is different depending on which way it's rotated.
Oh,
it's like a 6 this way, and then it's like a 3 this way.
Oh, wow.
Yeah. So I didn't know that.
That's a cool fact. Seems very useful. Yeah.
Thank you. Well, you're welcome to pick one of these out. That is all of the questions I have, or you can ask me questions.
Oh, what attracted you to geology?
Oh boy. I took a career test from a Army base ammunition plant. So I live in McAllister. That's where the Army base is, and they do a ton of recruiting out of the McAllister High School. So they come in junior year, and you take this really long test, and it like assesses your skills and what you're good at and all these things.
Wow.
And I had like 5 different things pop up, but the number one was geoscience.
Wow.
So
would you have ever thought to major in it if that hadn't happened?
I didn't know it was a career that you could go into. I didn't know that you could look at rocks and make money off of it.
Well, that's something that is really, I think, sad about right now, right today. So, the environment is like number one, right? The greatest crisis facing humanity is is how to live sustainably on the planet,
Mm-hmm.
right? And that's all about geosciences.
Mm-hmm.
And it's sad that somehow we don't teach it in high school.
Yeah.
Most high schools, you don't get exposed to it, so people don't get that it's a massive science that's relevant to their lives.
Mm-hmm.
And I wish that we could change that.
Yeah.
Because to me it's such a fun science because it incorporates all the other sciences, right? And it incorporates all the other sciences. It's extremely creative. You have to think about things that happened a long time ago in some cases, right? And try to make up the best story that you can,
Mm-hmm.
which has an element of fun to it. But anyway, I wish that it were taught in high school because I think that that's the problem, that students don't get exposed to it. I didn't
Mhm.
get exposed to it. Mike did because he went to a school where it was taught, but most schools don't teach it, and it's a shame.
It is a shame because I feel like it gives that real world application to a lot of different sciences. Like when I was doing my gen eds and I did my physics and my calculus, and it was all like, why am I learning these things? Like, I
Right.
don't need these. But once I got into my upper level geology classes and incorporated how the physics really does affect the rocks, and then you can see the
Mhm.
forces when you have little faults, or
Right.
it just really tied everything together for me.
Right, and it takes a long time to get there. I think we lose a lot of students early on because they're like, I don't want to do this anymore, these physics classes and so forth. And you've got to get past that, and then it's so much fun, I think.
Mhm. Yeah.
Oh, I have my other meeting, so I'm going to run off.
Okay.
Well, this was fun.
Yeah, thank you so much.
Okay, and I get to pick a rock.
Yes, pick your rock.
I think this one is really nice, actually. I'm going to go for that.
All right.
Thanks a lot. I love that it's Kyanite Day. See you later, friend.
Bye.